So I was just going through one of the older book that I own, and it goes by the name Elements of Programming Interviews, EPI for short, and you can see that probably. So this is a very nice book for uh, learning algorithms, learning tricky questions, and also it has a very good amount of questions being asked, um, which probably is asked on bigger tech companies, and if you're actually preparing for it, it will be really helpful. Um, but alternatively, you can actually use this to test yourself on how much you know about uh, primitive things, right? Like arrays or linked list or stack queues, for example, or graphs or trees. Even the trivial concepts are explained in form of a question, which can really help. So uh, I have done quite a good amount of read of this book for the last I guess 3 4 years that I have. And there is one problem that I was just reading through, which I came across again. I did it some time back, but um, it's really interesting. It goes by the name of Dutch national flag problem. It is on the first page itself of array chapter. So if you go inside, you would see. So you have some, you know, diagrams as well, which you can see. So this is more like a problem for explaining the concept of array, and it uses array basically as the data structure to uh, run the code, and it is based on the partitioning uh, concept, and the way we can partition a given array into three different sections. So why it is Dutch national flag problem is because um, the Dutch national flag contains of three colors basically. I believe, yeah, so Dutch national flag is having, I believe, three colors, you see, red, white, and blue. And all of them are equally spaced. So, it clearly represents a sort of a partitioning, which we are going to discuss. So, so it is just, Dutch or Denmark has nothing to do with it, but it's just a way to explain how we partition things into three different sections. So in this case, for example, we would consider, let's say, a list of numbers, and let's say you're given a list of numbers where you have the numbers which has to be partitioned in three sections. So for example, you may be given any set of three numbers, right? Let's say 1 2 3, and you have to specify the ones in the first section, the two in the second section, and the threes in the third section, right? It may happen in any of the business scenarios or something. So it is not particularly limited to any specific set of numbers, but yeah, I mean, you need to divide the whole array space into three different sections. So if you imagine it this way, it can be actually, if you don't want to think in terms of numbers, actually you can think of three sections. One section which is less than a particular value, one section which is actually equal to the specific value, and one section which is more than that value. So it covers basically the inequalities, right? So when we are considering any number x, so we can have any set of numbers x, any set of numbers, let's say x1, which is less than x, um, any set of x numbers, again, the duplicates, and any set of x2 numbers which are more than x. So it is somewhat like this. For example, just to explain you a bit, um, okay, so we can have something like, let's say, we have, um, let's say the number is 5, right? So 5 is somewhere here. So we have 4, we have 3, we have 2, and we have 1. Let's consider all natural numbers. So this section on the left, which is 4 section. 5 itself is the mid section, which is just equal to the value, which is the partition index or the pivot index. And we have, let's say, 6, 7, 8, 9, and 10. So this whole section on the right is the numbers which are greater than 5. On the left hand side, we have the numbers which are lesser than 5. So you basically partitioned it in such a way that you have all the numbers in the correct section. So you won't have a 3 which goes here, right? So imagine if something is like this. So it is not sectioned properly. It is not in its correct slot. So 1 to 4 is proper, but 3 is misplaced. So in this case, 3 should be shifted to this location. So this is how you partition it. So it is more like the way you imagine it. It can be any sort of three partition where um, you are partitioning the whole array space into three sections. Okay, so it can be anything. It can be low or high. It can be the value itself. I mean, if you have a particular rule by which a particular value should be lesser than that, it may not be actual number itself. So when we are considering a business scenario, when a particular section of employees, or let's say any sort of orders should be before this a particular section. It can be like, let's say, this particular department of employees should be placed right in between, and there should be this set of employees who has to be placed towards the left, or maybe the left wing of the employees in the midsection, and there are set of employees which goes to the right. So you can imagine all sorts of possible business scenarios if you are working on projects. But this is a very a minimal um, case where we are trying to partition the array space into three different sections. So what is the approach now? So now that we have understood what is the problem, what would be the approach to solve it? One way to approach is to go through all the elements and prepare three different arrays. Like we have left array. um, okay, so we have something like, so left array will be initially empty, then we have a right array which also would be empty, right? And we have in between we have the pivot array, which is the actual point where you want to partition the array with. So pivot array will contain only 5 in this case. So if there are multiple 5s in this array, 5, 5, 5 will be there. And left array would be like 1, 2, 3, 4, something like this. And on the right side we have 6, 7, 8, and 9, something like this, right? So the way it is partitioned, right? Now to form the left array, again you have to go to iterate the whole array and pick those elements which are less than 5. Now this I have given a very basic example where the array is already sorted. It may not be sorted. You may have 1 somewhere here, you may have 10 somewhere here, so it is not necessary that it is sorted. So definitely for each of these arrays creation, you have to go from one into the other by iterating all the elements. So what would be the time complexity and space complexity? So time would be definitely n, because for each iteration you are just moving ahead with n moves. So we have this whole left array creation would take O of n, right? Similarly, it goes with this. We have O of n here as well, because we have to form all the elements. We can't just uh, store, or this can be done as part of the left array iteration also. I mean, the moment you see, because it's just a single value, so the moment you see a 5, you update the pivot array also. But again, that doesn't matter much, because even if you are saving some time, it still will be O of n. So this again would be O of n. So if you take the whole time complexity, it will be O of n. But the interesting part is what will be the space complexity of it. So you are forming three different arrays, and you are trying to merge all of these arrays into one single final array, which will be the answer. So there you are trying to create three different arrays, right? So again, the space complexity also turns out to be O of n, because in the worst case you may have one of the right array, I mean either of these arrays, let's say there is only one of the element which is larger than the particular element. Let's say there is no 7, 8, 9, 10, you have only 6 over here. So you will have all the elements um, from the left covering most of the area, and the right covering only one. So similarly, there can be a right array, which will be too high. So in the worst case, I mean, if you take the big O, it will be spaces also. So time and space both would be O of n, which is something which uh, is fine. I mean, it runs in O of n, already good. We don't have any exponential or any sort of quadratic time, so this is already good. We can't do it in log n. Think about it, because um, we can't just divide the array or somehow reduce the work on sub problems, because they are all they're not exactly they are basically independent. There is no such relation between it, right? When you divide the array, you may not be aware, because this is not even sorted array, so you're not sure that whether the left array which you got for after division is the array which contains the smaller elements, and the right array contains the lesser element, because it will not be sorted definitely. So there is no chance of using a, a log n approach to solve this problem. But definitely we can do something about this space, right? We have O of n space, so can we do it in place, right? So this is a problem. Now, one of the possible approaches mm, can be that if we do it in place, right? I mean, that obviously means that we don't require any external space. So we try to, so our target is to make the space complexity O of 1, right? So this is our target. Okay. So this is our target. So to make it O of 1, what we need to do, what we can think of is, one way we can think of it is, when we are iterating from the left to the right, right? So we can definitely, how we manually do is, we see the numbers. So if you see, like for example, let's say it was reverse sorted, maybe let's say 2 and 3 would be probably here. Okay. And 5 is the pivot, so we start with 1, and 1 is already less than 5, so this is at its correct position, so we move ahead and we go to 4. Now 4 is also less than 5, so it is at its correct position. So 5 we don't touch anything, but let's move ahead. Now 6 is higher than the number, right? So for instance, let's skip this also for now. I mean, okay, we are just concerned with all the smaller elements in the first look, right? First glance. So the next element that we see is 2. Now 2 is definitely less than 5, so it has to be replaced somewhere, right? And we don't know where to replace it. So there is a problem here. Now 3 is also less than 5, so it has to be replaced somewhere, but we don't know where. So can we do it this way, that if for some reason, if we are able to iterate from left to right by having a fixed kind of an index where we actually replace the elements, right? So can we do it that way, right? That is the question. So turns out we can have one pointer which we can increment as soon as we uh, sort of uh, find an element which is at its which is less than the number. So in this case, what we can do is, we can keep a pointer, and we can increment it. So the main loop is already going from I0 to n. So we can increment a pointer from the pointer where we want to place the new element as, let's say, the index again. So again, just to reiterate what exactly I meant with this is, we start with index 0, and then we move ahead, right? And at the same time, if we keep a track of, let's say, I is equals to 0, which will be the main loop iterator, and we have another index, like for example, we have it for, again, starting with 0, right? So in the first place, what we do is we start the looping, and the, let's say, the first element is, like in this case, it is 1. So what happens to 1 is, it compares, it is less than 5, then it will just swap. So in this case, it will swap I with index. So since both of them are 1, it just moves ahead. So index will be now pointing to this 4, right? Because 1 is assumed to be at its correct position, and now it moves to the next element, which is 4, and 4 is less than 5, so it also tries to replace it with itself, uh, because I and index both are 1 here. Now 5 on the other side is equal to the pivot, basically in this case 5. So what it does is it just updates I, but it still remains, the index still remains the same, 5, right? So what about 6, right? We just skip it. As I told, we just skip the first pass where we are just considering the left pass. We are going from left to right to sort all the array elements which are less than a particular pivot to the left. So in the first pass, that is what we are targeting. So we move to 6. Now 6 is more than 5, so we just move ahead, and then we come across 2. Now you remember we kept index as index pointing to this element, right? Third element. So we would just swap this. Now the moment we swap it, index will move to the next position, which is 6, right? So here 2 will come, so it will be more like 1 4 and 2, and this is obviously 6, so 6 will remain at its position. Now 2 will become 5, and we have the last element as 3. So now in this, after this case, I moves to the next position, and index moves to 6. At this position, we encounter 3. Now 3 is again less than 5, so what it will do, it will swap the position back. So it will be more like 1 4 2 and 3, and we have 5 and a 6. So you see, in this case it happened to be like 5 and 6 are already in place, I mean, based on this. But uh, you can see this, right? All the left section are less than 5, and the right section is more than 5, and obviously 5 is in the middle. So this is how we approach. And but in this case, it happened to have been sorted already. But imagine if there is set of elements which are towards the right, which again needs to be sorted, right? So there can be, let's say, a 5 6 and a 5 after this. Okay, it can happen. Now how to sort that also, because now we need to club all these fives into one place. But there's one small observation here, that once you do this, right, if you are even doing this, let's say there are more elements to it, right? 7, and there is a 5 again. So when you're doing this back, right, so you don't need to encounter these 1 4 2 3 again, because these are already happened. These have already moved to their correct positions. So what you want to do is you have to go till the elements which are equal to or greater than the pivot. The moment you encounter a number which is less than the number, the pivot, then that means you are entering the region where you have already done the ordering. So this is the approach, and this happens to solve it in place with obviously constant space, and again it takes n O of n times iteration, because we are iterating left and right in the array, so it is close to O of n itself. I mean, even if we are close, in the right pass, we are only iterating it till the point where we reach a point where we get the element which is less than that, but still it is again order of n. So uh, so to solve it, right, so we will let's actually solve it. So this is the approach that we have finalized. So let's see if we can solve it. So I'll just name the file Dutch flag dot, and I'll do it in Python. You can choose any language, but it is much simpler because it has a very less boilerplate code kind of, so you can directly go ahead and implement the actual function. So first of all, let's make the function as, let's say, shuffle maybe, and we have two elements here, array and the size of the array. Okay. Okay, so the first thing that we want to do is we have to declare, as I told, we have to create a the pointer that actually tracks, or the index which tracks where to replace it. So we will name it index for simplicity, and we have another variable I which basically does the iteration from the left side of the left pass basically. So we will proceed with the left pass now, or I shall mention a comment here as the left pass. Okay. Now what next? So we have already initialized all these variables. Now the next thing I can do is maybe have a while loop, and what will be the condition? While I is less than n, because it will go all the way till the end to track any element. And the next thing would be checking, right? So if ARR of let's say I is is greater than is less than 1. Okay, before we actually proceed with the context, let's define it. So let's have a list. Okay, just because I'm trying to do it with 0, 1 and 2, because that is what is available in most of the I believe the book example also deals with 0, 1 and 2. um, Alternatively, you can do it with any sort of things, but it is assumed that you already know the pivot from which you are trying to the pivot basically is known. Or we can also pass the pivot here, so we can just do that. So maybe let's pass the pivot in the method itself. So pivot, and we will name it as pivot. Okay, so we'll create the array once we do the code, because that we can do it on the fly also. So we have array of I is less than pivot, and what happens next? So we discussed that if the element is less than pivot, so what we do is we shuffle it, right? So now shuffling is again a very interesting part in Python. We can just directly do it as a common thing. I mean, we can have array of index, and we can just give array of index comma array of I. This will work. Now what will be next? Index will become plus equals to 1, and yes. So and what about I has to also increase, right? So I plus equals to 1. So now this is the array, right? This is the first part where we completed the left pass. Now for checking this, we can actually print this to see if we have done the left pass successfully. So we can just do ARR, and we can just pass the call the method shuffle, and let's imagine uh, a sort of a 0, 1 array. So let's say 0, 1, maybe 1, 0, and what we can have 1, um, 2, 1, 2, again 1, 2, and maybe let's say 0, 0, 0, 1. Okay, let's say. So how many elements are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 elements. So that will be the first parameter to this, and 12, and the pivot as we have selected is 1. So let's do that, and let's call this, right? So what we have to do here is we have to write Python Dutch flag. So you can see once this is done, we have all the zeros shifted towards the left, right? Just don't bother about 2 and 1, but you see the left section already sorted here, right? So this is a good point that we have already done the left pass. Now we have to do the right pass as well, because there are 2 and 1s, incorrectly arranged. So 1 has to move towards the middle, and 2 will be shifted towards the right. So all the 2s and 1s are in not the proper order. So there is no such partitioning here. So we have to do one right pass again. So we can just comment it here and make it right pass. Now what will be the condition in this case? So first of all, where should we move from? We should move from the right to the left, because there is no point moving from left to right, because the left portion is already sorted. So shall we initialize index as n minus 1, right? And what about I, right? We can reuse I, because this job is done. So we can have I equals to n minus 1. So both of them point to the last element now, right? So why we are going with the last? Because we have some elements which are yet to be sorted towards the right portion of the array, and that we need to do, right? So the next thing is we can give a condition. Sorry. Oh. Okay, So we have to give while, and what would be the condition here? So the condition may be, um, we have to stop the moment the element becomes lesser than the pivot, right? So we can just do while a array of I is greater than equals to pivot. We have to do this, right? So this will be the continue condition for this while loop. And so the condition again will be if ARR of I is greater than 1. Remember we did the reverse for the left side here. Okay, oh, pivot, right? We are passing pivot here. So if this is the case, then again the same thing which we did, we can just copy paste this whole part. Okay, there has to be indentation as well. And we just replace this whole thing here. And what we do is we do index minus equals to 1 because we are subtracting going from the right to the left, and in either of the cases I minus equals to 1 will happen, right? And so this is the right pass which is already done now, and let's print the array now and let's see if it works. So we can just do this. Yeah, you see this. Why there are two times? Okay, this has to be okay. Anyways, it is for easy reference. You can see the first part which is printed over here is the left pass, right? So you see 2 1 2 1 1 1 1 is not in the proper order. So after the right pass does complete, we have all the ones shifted towards the middle and the two shifted towards the right. So this whole thing runs on O of n, but it uses 0 extra spaces. So we are not actually declaring any new array or any sort of, we are just doing it in place. So this actually runs in the same time complexity as you would run by creating three different arrays, but the space is much more reduced here because we are trying to have all these swapping done in place, right? So this was a very intuitive problem to me. I really liked it because many a times we are not concerned much about the spaces, but this is one of the problem where it is good to know that you can reduce it, reduce the space to some extent, and which actually gives you an optimal solution. Yeah. So again, so with this approach we have time and space both. So time is O of n, right? And the space, since we are doing it in linear time, sorry, we are not initializing any new variable, so we have O of 1. So this is the Dutch flag problem. I hope you understood and you liked it. You know, for any such clarification related to the code or any such algorithmic questions that you have, you can ask me in the comments, and I'll probably be posting few of more because as soon as I read a thing and I remember recollecting it, solving it or something, or even if I have not solved it, I'll try to solve it with you live the next time. So I'll be adding more videos on this. So yeah, so stay tuned and